All right, welcome. Good to see you guys today. We are going to be talking about binary ionic compounds and ternary ionic compounds. The title here says actually nomenclature. Nomenclature is the idea of naming things. That's an M. So nomenclature is the idea of naming. We will go beyond naming and we will talk about how these ionic compounds are formed, how we can write down their formulas, and how we can name the compounds. The first type of ionic compound we're going to talk about is a binary ionic compound. When I say binary, what does that make you think of? Yeah, two. And so we will be talking about that. When I say the word ionic, okay, that's going to bring up something different. What does that remind you about?
Like isotope, I've heard this word before.
Yeah, it's not isotopes. Ions. Okay.
Do you write any of this stuff down?
Yeah, you may absolutely write this. I was saying that just copying the words that are on the screen would not really be the notes. All right. So as we talk about, what I want to talk about first before we go into how ions can form ionic compounds, let's just talk about what an ion is. All right. So let's take a moment and have a little conversation about that. Bless you. Bless you again.
I did not have to run.
All right. Hey, what is an ion? All right. Tell me again, Madison. Okay. It is an electrically charged atom or a charged atom. I'll say an electrically, since I already had the an up there, an electrically charged atom due to what causes an ion? Yeah. A gain or loss of electrons, which I'm just going to represent with the E minus sign. And so we've got an ion as an electrically charged atom. That is not what I meant to do, but it's kind of a nice color. I don't know. Nobody really likes that color. Electrically charged atom due to a gain or loss of electrons. Now, if you gain electrons, what will your overall charge be? Ooh, except electrons have... Ooh. All right, so let's look at it this way. Let's just say that I have I'm going to pick boron. Let's just say that I have a boron atom. And boron is what atomic number?
5.
All right, it is an atomic number of 5. And so, so I should have written that down there. What is boron's mass?
It's 11.
All right, so technically we would write it like that. Now, since its atomic number is 5, that means in a neutral atom it will have 5 protons, which I'm just going to represent here in the nucleus. And then around the outside, first in the first 1s orbital, we would have 2 electrons. Ooh, I was doing well for a little while. And then 3 more in the 2s 2p orbital, so in the second orbital. Again, this is not at all how this is a little more of the Bohr model. This is not at all how they actually are found in the atom, but this will give us a little representation that'll let us talk about something. So nice. So if we've got 5 protons and 1, 2, 3, 4, 5 electrons, what will the overall charge be? Yeah, the overall charge will be 0, and so that atom will be neutral. Now, what if I were to, and this wouldn't happen with this electron, with this atom, but what if I were to gain another electron? Ooh, now it's got 5 pluses and 1, 2, 3, 4, 5, 6 minuses. So it would have an overall negative charge. What if it gained another electron? Then that would be a -2. So do you see how that by gaining electrons, we actually get a negative charge? Okay, so as we gain electrons, we actually create a negative charge. Okay, now what if I were to, so right now I've got 5 protons, and this is much more likely to happen with boron. What if I just lost one of those electrons? A loss of electrons would actually then produce a positive charge or a positive ion. Okay? So you can either remember that electrically, saying, hey, if I gain more negatives, I'm going to have an overall negative charge. Hey, but if you lose some negatives, then there's a more positive result. That is like if you break up with someone or end a friendship that was just negative, it was real toxic, all right? Hey, if you get rid of that negativity in your life, you are a more positive person. So losing negativity, all right, creates a positive result. You just remember that, life lessons right here in chemistry, okay? So there's wisdom everywhere to be found, my friends. So anyway, that is that. So gaining electrons, negative, and losing electrons, positive. Now, some people have asked, hey, what about the protons? Could we gain and lose protons? And the answer is no. We are not going to be doing that because the protons are found here in the nucleus. We are not going to be messing with the nucleus because if you change the number of protons in the nucleus, you are changing the fundamental nature of the atom. It would no longer be boron. It would be something else entirely. All right? And so we are not going to be changing the number of protons. We are going to be changing the number of electrons. And as we do, that gain will create a negative ion, and a loss will create a positive ion. By the way, we call a negative ion an anion, and we call a positive ion a cation. All right, and again, you can see the T sort of resembles a plus, and maybe that'll help you to remember that a cation is positive.
Question though, you remember when you said if you change a proton, you change the fundamental?
Yes.
Well, I remember seeing a picture on the internet that says it was like super controversial though, and basically something about like converting lead to gold though. Like how's that controversial?
Well, it's controversial in the sense that we don't have a good way to do that. That was the fundamental goal of alchemy, where by ordinary chemical means, alchemists hoped to transmute lead into gold, something very common and non-valuable, into a very valuable commodity. And that does not happen through ordinary chemical means. That happens through either radioactive processes or nuclear chemistry with nuclear processes. So that is not a part of our ordinary chemistry.
Oh, okay.
Yes, sir.
Like, say, for hydrogen specifically, could you lose the electron and have 0 electrons?
All right. So hydrogen, yeah. If you lose the electron, then you just have a proton, and if you lose that electron, then you have just a proton, and that's an H plus. And so that is actually something that happens often.
So an atom can have 0 electrons?
In the case of hydrogen. All right, let's press on. So an ion is an electrically charged atom that gains or loses electrons. So let's talk just for a moment about let's talk for a moment about life goals. Okay, so kind of just create an area here where we can discuss some goals. Now we are not going to discuss your life goals or my life goals. We are going to discuss the life goals of atoms. What is an atom's life goal? So an atom's life goal is exactly as you guys have said, to be fulfilled. You can. Fulfilled, is it 2 L's? I don't know. I think it's only one. To be fulfilled. To be stable. All right? Both of those are, you could say, to be happy. And both of those are excellent life goals for our atom. And the way that that's going to happen is by fulfilling or satisfying the octet rule. Ooh, satisfy the octet rule. All right, and I'm just going to maybe circle that in a nice golden color. All right. So the atom's life goal is, in fact, to be happy and stable, and the way that it does that is by satisfying the octet rule. And the octet rule means what? For it to have a full valence shell, which usually will mean 8. In the case of helium or hydrogen, it means 2. All right. So to satisfy the octet rule, which I'm just going to say is 8 valence electrons in the outer shell. Eight valence electrons in the outer shell, or in the outermost shell. All right, so 8 electrons in the outer shell. Boom. All right, questions about that? Now, there's a couple of ways that this can happen. So let's talk about, let's choose a couple of atoms and talk about how that could happen. I'm just going to rope off some space here. So let's talk about our friend chlorine. All right, so if I have a chlorine atom, now, if I have an atom, remember that's going to be electrically neutral. All right, so I've got a chlorine atom, which means same number of protons as electrons. What is chlorine's atomic number? 17, so it's going to have 17 protons and 17 electrons. Okay? And now, what family group is it in? If you look at the periodic table and look at the top of the column, what family group? All right, it is in the halogen family. That is group 17. However, in a more relevant way for us, it is group 7A. Okay, so group 7. Now that means that it has 7 valence electrons. So I'm just going to make a quick little note that chlorine has 7 valence electrons. Yes, ma'am?
So is each element have the same electrons as protons?
In a neutral atom, it absolutely does. Now remember, if it's an ion, then it's going to be charged because it's going to have different numbers. Okay? It could have more, it could have fewer. All right? But in an electrically neutral atom, which is just what we generate, if I say, hey, talk to me about a chlorine atom, it means an electrically neutral atom. And so that's going to have, in this case, it's in group 7, and so you say, hey, there's 7 valence electrons. Let me show you another way that we can know. Let's talk about the electron configuration for chlorine real quick. Let's see.
I have a question
Is there, okay, so there's a couple of questions before we talk about the electron configuration. Go ahead.
Can I go use the restroom?
Oh my gosh, you're killing me. You kill me. Fine, go.
Okay, so, wait, I thought y'all said it's in the 17th.
My question was.
Okay. So, so if you look at the top, of that next to last column, the halogen column, if you find right at the very top of it, there's a 17. And if you look on your periodic table, there's a 17. But then underneath that, there's a Roman numeral that says VII and an A. And that, of course, is the Roman numeral for 7. And so sometimes it is referred to as group 17. Sometimes it is referred to as group 7A. All right? 7A is actually more helpful because you can look and say, oh, it's in group 7A. It has 7 valence electrons. Whereas group 17 is not, as useful in terms of understanding the shortcuts about that. Hey, so go ahead.
Group 18 be group 8?
Yes, and so group 18 or group 8 is the noble gases, and they already have satisfied the octet rule because they have 8 valence electrons, and so they are happy and stable, and they are inert, meaning that they do not react for that exact reason. They are not interested in changing electrons or sharing or swapping. So they are inert and are non-reactive because they already have the octet rule satisfied just by themselves. All right, now I want us to look at the electron configuration for chlorine. All right, I'm going to write the whole thing out. You remember 1s2, 2s2, 2p6. Ooh, let's put those commas in there. 3s2, 3p5. All right, everyone see on our periodic table how those numbers came to be? And so as I look at this, I see, now, remember when I'm talking about the valence electrons, I'm talking about the outermost energy level. So the outermost energy level in this case is level 3. How many electrons are there in that outermost energy level?
There is
2 plus 5,
7.
7. Okay, so we can know that there are 7 valence electrons by looking at the fact that it's in group 7A. We can also know if we look at its electron configuration, we can see that that there are 7 in the outermost, which is the 3rd energy level for this one. So either way, now if it's going to get to the octet rule, if it's going to get 8, what does it need to do? What needs to happen for it? It needs to somehow come up with, that's right, one more electron. So it needs one more electron, okay? And it really wants that one more electron to finish filling this p orbital, or this p sublevel, okay? So that it can get to 3p6 and be like its good friend neon, full and complete and happy. All right? Now, if I give it one more electron, at that point it would have how many? All right, well, how many did it have here? It had 17 protons, and it had 7 valence, but 10 others, so 17 electrons. Do we recognize that it's a neutral atom? And so 17 protons means 17 electrons? But then we gain one more. And so now it's going to have 17 protons and 18 electrons, which means it will have an overall charge of -1. Yes, yes? Yes. All right. And so it will have an overall charge of -1. And that is because it gained one electron. All right. What about, so let's see if we can find another friend, let's see, let's just rope this off real quick. Whoops. Wasn't supposed to do that. I'm gonna get rid of that boron atom. Sorry, boron. We're done. You're a good friend. And okay, yeah. Away we go. All right, here we go. Yeah, except for this one little. I'm just gonna leave that there to remind us of the good times we had. All right. Hey, what if we look at instead of looking at chlorine, what if we look at let's look at oxygen.
Iodine.
No oxygen. Thanks for checking though.
What if we do noble gas next?
What if we do oxygen next? Hey, so I'm gonna pick oxygen. Okay. I'll look at a noble gas with you in just a second. Now, oxygen, what group is it in? Okay, it's in group 6A, which means that it has 6 valence electrons. Okay. So oxygen is in group 6A, 6 valence electrons. What is it trying to get to? Yeah, really trying to get to 8. Okay. And so it is absolutely trying to make its way to 8. What's it going to have to do in order to do that? Gain 2 more, which would mean, or lose 6. Here's what I'll tell you though. It's going to be super hard to lose 6 electrons. That's just tough to do. I'm not going to say it's impossible, but it would be super tough to do, and it's not going to happen naturally. That's not going to be a natural energetic process.
It has to be done by man?
It would have to be done by extraordinary means. We would have to, that's not just going to happen through regular chemical reactions. Okay? Hey, going to press on. So oxygen then is going to be a -2 because it would actually have to, in order to transition from 6 to 8, it would have to gain 2 more electrons, which would give it a -2 charge. Yes? Yeah, feeling good about that? All right, excellent. So that is how that happens. Hey, what if we look to the other side of the periodic table and look at potassium? Everyone see the potassium? Find it. Letter P. No, it's not letter P. That's phosphorus. What is potassium? Yeah, K. Which, interestingly enough, in the Latin is kalemia. And that was its original Latin name, which is why it is a K in the periodic table. All right. So, now, so let's look at that. What, again, what group is it in? Yeah, group 1A, which means 1 valence electron. And Andrew, just as I told you earlier, that you're not real likely to just lose 6 electrons. Well, you're not real likely to just gain 7 either. Okay? And so this guy's chance of getting from 1 valence electron to 8 valence electrons to satisfy the octet rule, no. Okay? That is not going to happen. All right? He is not going to just find 7 electrons sitting around. Ain't happening. All right? Oh, but here's what else can happen. Let's write the electron configuration again just for fun. 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s1. Okay, because we just have that one little electron left on the 19. Hey, now, here's something that we could do. Okay, we can't gain 7 to fill up that 4th energy level and get a valence electron there. But there's only 1 in this 4th level. What if we just sort of scrubbed that out? In other words, what if we lost that electron? I know. Absolutely. Now, hey, if we did that, do you see that our outermost energy level at that time would be 3? And we actually would have a 2 and a 6 for a total of 8, which would satisfy the octet rule.
Whoa.
Yes, it's true. Okay? And so you have 2 ways that you can satisfy the octet rule, either by climbing the ladder and gaining more electrons to fill that outer shell, or by dropping electrons and dropping down to the next inner level, which then is your valence shell, and having it already be full. All right? So what if you already had it filled to begin with? All right, so let's examine happy little neon. Okay, neon is in group
18.
Group 18 or group 8A, which means it has 8 valence electrons. And neon, since it already has 8 valence electrons, has already satisfied the octet rule. It has no need to gain electrons or lose electrons. And in fact, if someone tries to push electrons off on it, it's like, no, I'm not taking your electrons. Take those things back. I got nothing to do with you.
So basically, all the noble gases should be fine if you don't do anything with them.
Yes, they are inert and are non-reactive with very, very few exceptions.
What are those few exceptions?
Not going to talk about it today.
I also have a question for you. It's just a,
Xenon and fluorine. We're not talking about it though.
I have a question.
All right, go ahead.
Do you know how Krypton became like Superman's weakness though? Like why they choose Krypton out of
Because, well, I don't know why they chose it, but it was because he was from the planet Krypton, and so it has special powers
Yeah, but
over
what's Krypton do in real life,
Superman. All right. In real life, it just kind of sits there because it's a noble gas.
Yeah, that's what I'm
All right. Yeah. Nothing. You're much worse off with lead or other heavy metals. All right. Hey, so we are heavy metal, like songs from the '80s. All right, we're moving on.
Or the movie that came out.
That too. All right. Let's see. Let's go back to our previous. And I'm just going to warn you, this is going to be a shock to the eyes when I.
Go back.
Yeah. And you thought I was kidding. That's quite a little jolt there. So when we look at binary compounds, binary ionic compounds, what we're going to do is we're going to have 2 elements from the periodic table, usually a metal and a non-metal. Okay. So metal and a non-metal. So let's go to the periodic table just for a moment. And I'm going to remind you that we've got some metals over here on the left-hand side. And then we've got some non-metals over here on the right-hand side. The noble gases are inert and non-reactive because they've already got their valence shell completely filled. And then we've got some highlighted in pink here, some metalloids that are sort of metallish, sort of not.
Metallish.
They have some characteristics of metals and some not. So they're like those hard rock wannabe groups that aren't really metals but try to be.
Are you calling someone out this week?
I'm not going to mention any particular bands. All right. Not talking about it. Hey, so Diego, we are going to look at. I'm going to choose one metal from over on this side, sodium. And I'm going to choose a non-metal from this side, chlorine. I know. Wow, Mr. Willis, how did you circle those so fast? I am speedy. So if we take then our sodium, okay, and I'm going to write the metal symbol. Now, which group was sodium in? The alkali metals. It was in group 1A. So what charge would it have? Yeah, +1, because it will lose 1 electron to satisfy its octet. And so it will be +1 at that point. Then I'm going to write our non-metal symbol, our chlorine. All right. And what is its charge?
7.
Okay, it has 7 valence electrons, which means it will get 1 more, and when it gains 1 more electron, it will have a charge of -1, because as it gains that 1 electron, it will have a negative overall charge, -1. All right, now let me ask you this. Okay, and I'm actually going to go back to our other page for just a moment. Okay, so forget all that. I told you, speedy. So let's look at our Na plus and our Cl minus that we began discussing on the previous page. Hey, what do we know about oppositely charged electrical particles? They attract each other.
So opposites attract, basically?
So opposites attract, okay? It's true in life, it's true in chemistry, all right? All right, and those two are then going to zap together and actually bond.
Is that where salt comes from?
And that is actually where the salt sodium chloride comes from, is you have some, and here I want you to see this, it's because it's such a perfect partnership. We've got sodium, and if I drew its Lewis dot diagram, we would see it with 1 electron. Chlorine, remember, since it has 7 valence electrons, we've got those around the outside. Chlorine's like, oh man, if I could just get 1 more electron to fill up that valence shell, and sodium's like, oh, if I could just get rid of this 1 electron so that then I could drop down a level and everything would be cool. And chlorine's like, hey, if you're not using that electron, and sodium's like, well, sure, go ahead.
So that's how they make salt?
And that is actually how many things bond together, is that electron is then transferred from one to the other, and then we've got our positive ion and our negative ion, which then attract electrically and bond together as NaCl. Now, yeah, aka sodium chloride. All right. Now, in this case, since this was a +1 and a -1, we only needed 1 of each. Okay, and we couldn't label that with 1 of each, except we don't do that in chemistry. All right. We don't put the ones on there. If there is not a number, 1 is implied. Okay? So if there's not a number, 1 is implied. All right? Now, what if, let's look at this a little differently. Let's look at it this time with a different friend, calcium. Okay? And we'll keep chlorine. All right? Now, calcium, which group is it in? All right, it's in group 2A, which means it has 2 valence electrons, and so when it loses those 2 valence electrons to satisfy its octet, it wants to lose those 2 and become what charge? It wants to lose electrons, so that will be a plus, and it wants to lose 2, so it will be a +2. Okay? Yeah, we're losing electrons, which means positive charge, +2. Chlorine, group 7A, looking to make the jump over to that noble gas. It's looking to gain 1 more. And so it would be a -1. Excellent. Now here's the thing. Okay, you've got calcium. Calcium needs a pair of electrons. Or excuse me, calcium has 2 extra electrons that it is trying to get rid of. Chlorine's like, hey, I'll take 1 of your electrons. Calcium's like, I need to get rid of both. Chlorine's like, I'm only taking 1. Calcium's like, it's no deal then. All right, it's all or nothing. Chlorine says, but what if I brought a friend? And you could give 1 of your electrons to me and 1 of your electrons to my friend. That would work. All right. And at that point, calcium is willing and able to donate 2 electrons, 1 of which is received by this chlorine and 1 of which is received by that one. And so you end up with calcium chloride. Ooh, except how many calciums did we need?
2.
Whoops, it has a +2 charge, but I only needed, just count the ones that are up here. 1. All right. Oh, but we don't put that 1 on there. How many chlorines did we need?
2.
And so it's CaCl2, calcium chloride. All right. But that's the reason that we have to have 2, is so that this -1 and this -1 will account for and match up with that +2. All right? And a lot of times what people will do is they'll say, okay, calcium, chlorine, and then they'll just kind of swap the numbers this way and get Ca1 Cl2, all right, and that's how we end up with our chemical formula, all right. But the reason that it actually works this way is because we need 2 chlorines in order to be able to fully account for the 2 electrons that calcium wants to donate. Questions about that? All right, if there's no questions, then I'm going to ask a question. What about calcium and oxygen? What's calcium's charge?
+2.
We remember from just above here that it was +2. What about oxygen? It is in the group 6A, and so it's going to take on 2 electrons and become a -2. Ooh, +2 -2.
Equals 0.
So would that be Ca2O2? No, we don't need 2 of each.
Wouldn't that equal 0 though? I remember that from math.
It's just going to be CaO, because this donation of 2 electrons exactly meets up with this need for 2 electrons. It is a match made in heaven. Now, Eliana, what I will tell you is that that we want the net total to be 0, okay? Because we want the number of plus, which comes from donation, to be the to match the number of minus, which comes from receiving. All right, and so we do want the total, if you just add up the charges, to be 0.
Yeah, but I was just thinking, isn't that just like math though? Because I remember like in math.
It's just like math, just math. And so we would actually get a calcium oxide, CaO. Ooh, what if I had some aluminum and some oxygen? All right. What group is aluminum in?
3.
It's actually in 3A, which means it's going to want to give up 3 electrons and become a +3. What about oxygen? Still a -2 or a 2-. And it doesn't matter which way you write it. Some people are concerned that if you write it this way, that it will look like a math problem. And so they prefer to write it with the number first and then the charge. I don't really care, and I don't feel that way. So sometimes I will write +2 and -1. Other times I will write 3 plus and 2 minus.
Did you ever do good math though?
I did all right. I made it just fine.
No.
Hey, now, aluminum +3, oxygen -2. All right? So aluminum's looking to donate 3 electrons. Oxygen's only willing to accept 2. So we bring another oxygen along. All right, well now we've got 1, 2, 3, whoops, but we need a 4th one. Aluminum's like, nah, only 3. So let's bring along another aluminum. Well, great. Now we're up to 1, 2, 3, 4, and then we've got 2 more. Oh, I think I see a solution.
That's crazy.
I know. Crazy times, my friend. And again, 6 donations, 6 acceptance. And again, if I just wrote Al3 plus and O2 minus and did my little crisscross, then I would get Al2O3, which is exactly what we see if we did the individual groupings as well. 2 aluminums, 3 oxygens, 2 aluminums, 3 oxygens. Yay. All right, questions about that? Let's go back to our other page for a moment. Cover your eyes. Bam. I know. So what about naming the compound? So this goes back to what we said a second ago, that the charges must zero out. Okay, and so we must end up with a they must zero out total, and that's what this is telling us. And then we write our formula using the subscripts, NaCl, or let's see, what did we do on the other page? We did calcium chloride, CaCl2, or CaO, or Al2O3, any of those, and that just tells you the number of atoms of each type.
Can you go up a little bit? I was miswriting something.
I'm sorry?
Can you go up a little bit? I was miswriting something.
Can I go up a little bit?
Yeah, just a little bit. No, I meant the other way.
Okay.
Yeah, that's good, that's good.
All right, there we go.
Good, good.
Hey, let's name the compound. What we do is we name our metal first. Let's see, I'm going to just go basic. Name the metal first. So I'm just gonna choose this one. Metal first, calcium. And then name the non-metal, chlorine. And then change the ending to "ide." Okay? So instead of calcium chlorine, it's calcium chloride. Okay, I know, calcium chloride. This would be sodium chloride. This would be calcium oxide. This would be aluminum oxide. Okay?
Should we write how to write the formula, how to name the compound?
Let's go ahead and write that down. Name the metal, name the non-metal, and change the ending to "ide." All right, so let's write that down, and I will scroll that up to make it just a bit easier to see.
I'm just curious if we could just take a picture real quick.
Go ahead.
Okay. That's fine.
Yes, sir.
Will the taloids mix with either or neither?
Okay. Most of your metalloids will not form ionic bonds, and that's what we're talking about today. Today we're talking about ionic, which comes from ion, which comes from swapping electrons. Tomorrow we will talk about molecular or covalent, which is going to come from sharing electrons. So today we're just talking about swapping, and most of your metalloids will not be swappers. They will be sharers. Okay? So most of the time that's how that will work. All right, good question. All right, let's scroll on down. Okay, so I'm actually going to go here first. No, I'm not. I'm gonna go here. All right.
Is this the worksheet?
No, this is not the worksheet. I would like you to turn over your periodic table and look on the back side. There are some groups of atoms which move and interact as a team. Okay, and you can see some of those written on the back. There are several which have a -1 charge. Chlorates, bicarbonates, cyanide, bisulfate, hydroxides, nitrates, perchlorates. Cyanide's not good for you. It's poisonous. No, you're thinking about something else, but that's not good for you either. Excuse me. I know, a little cyanide.
You mentioned cyanide.
Hey, and so those actually move and transition as a team or as a group. And so we call them polyatomic ions because they actually act like an ion, but they are made up of more than one atom. So many atomed ions. Okay, polyatomic. So I do want you to be familiar with that term.
Polyatomic?
Polyatomic ions. All right? And it works exactly the same way. Let's say that I have a sodium with a +1 charge, and let's say that I have a chlorate, which is a ClO3. Now you'll notice that it's in parenthesis so that it can, so that we remember that it's not going to be breaking apart. It's going to be acting as a team. All right, and so we've got our chlorate with our -1. plus 1 minus 1. And so that's going to balance out and give us sodium chlorate. Ooh. Same thing that we talked about earlier. Magnesium has a plus 2. Carbonate has a minus 2. Well, this is a perfect pairing. Plus 2 and minus 2. And so again, we will just have Mg parenthesis CO3 close parenthesis and have a magnesium carbonate. But what if I have potassium, which you remember was a plus 1, and sulfate? Everybody find sulfate on the back of your periodic table, and you'll see that it is not in the minus 1 category. It's in the minus 2 category, which means that I would have to have 2 positive potassiums to accept or to donate the electrons for the 1 sulfate group, an SO4. And so again, 2 potassiums, K2, and then SO4 in parenthesis with that implied 1, which we don't write. All right, and that's going to be potassium sulfate. What about strontium hydroxide? Yes, same. I feel the same way. What about strontium hydroxide? Strontium, if we find it, it is in the group 2A, and so it's going to make a plus 2 ion. Hydroxide, if we find it, it's in the minus 1 ions category, which means I would have to have not 1 but 2 hydroxides in order to accept the donation from 1 strontium.
Hydroxide, is that where hydrogen peroxide comes from? Or?
A little different.
It sounds like
yeah, they do have similar endings. And so strontium, there is only 1 of them, but you'll notice that we have 2 hydroxides. And so again, you've got your open parenthesis, your hydroxide, and then your closed parenthesis, and then your 2. The 2 is on the outside of the parenthesis to indicate that there is 2 of everything on the inside. There are 2 hydroxides that are a part of this bonding. Okay? If there were no parentheses, then it would be 2 hydrogens. Do you see why the parenthesis is especially important? So that we can see, yes, that's a hydroxide, not just a pair of hydrogens. Okay? And this is going to continue to pair up the same way that we did earlier with our aluminum and our oxygen. We've got our calcium, again, our calcium plus 2, our phosphate minus 3, and if we cross the charges, we get Ca3PO4 2. All right? Everyone comfortable with how that's happening? The naming for this is even easier than the last one. Name the metal, name the ion. Okay, and that's all that there is to it. You do not have to make any adjustments to that. Here's what I will tell you. You always need to place the positive ion or the positive ion first. Question, Andrew? All right. If it comes up again, we'll. Excellent. Hey, so we are running short on time, so we're gonna rush through a couple of quick examples here. Strontium nitrate. You remember that strontium was Sr2+. Nitrate. Look on the back and find your nitrate. NO3, and it is a -1. Okay, which means then let's cross it up and we'll get strontium 1, which we won't write, and then nitrate, NO3 2. So there are 2 nitrate groups and 1 strontium group. All right, let's see. Let's do barium sulfate real quickly. And so barium also happens to be in the same group 2A. Find sulfate, please. We found it? SO4, is it 2 minus?
Yeah.
Okay, so I need to review my, I know, Mr. Willis, please. Whoop. 2 minus, and again, that ends up being a match made in heaven, a +2, a -2, so that will then just be barium sulfate, and we'll just leave it like that. Real quickly, the naming rules for us. A ternary ionic compound is 3 or more elements.
Should we write this down?
Let's do. Again, ionic means a metal plus a non-metal. The exception is that sometimes you'll have ammonium act as the cation, and so then it would be that polyatomic ion and a non-metal, or another polyatomic ion, which would be a non-metal. Hey, that's a key. Metal and non-metal. That's how you can, that's almost always what forms your ionic compound. Again, we're going to write the cation symbol, the anion symbol. If there's a polyatomic ion, we're going to put it in parentheses. The charge must equal 0, and we'll write the formula using the subscripts, just as we did above. And to name the compound, it's super easy because all you have to do is just write the name. Always put the cation first. The positive ion always comes first. And cation first, anion second, and just use the anion name from the chart.
Should we also write that for under there? Like,
Let's write it all, and then I will scroll down and allow you to see where it says to always put the cation first. All right. Okay. Normally I'm not a fan of picture taking, but we are almost out of time, and I did give you a lot of words there right at the end. So snap a quick photo. All right. Yes, sir.
The match anyway, just to make sure.
Go ahead.
Can a negative ion and a positive ion mix?
Well, yeah, that's what's always happening. It's just that we always name the positive first.
Well, I mean like the 2 and then the other 2.
Like a -2 and a +2?
Like in the bottom it says with more than one ionic charge, so like cupric ion and sulfate.
I'll tell you what, I'm going to address your question in just a moment. All right? Hey, don't put things up. We still have a couple more things to do. All right? Just listening, please. Positive ion always comes first. All right? That will conclude our recording, and I hope you're having a fabulous day.